Reading 3 sets of papers. Okay. All right. Welcome back, everybody. Math 107. We are at Lecture 10A. Last time we started in Section 3.6, we were looking at real zeros of the polynomial function. You remember that in Sections 3.1 and 2 and 3, 1 and 2, we looked at polynomials and the zeros were nice little integers. And what we're trying to do is build upon that and be able to look at when we have real zeros of the polynomial. Remembering a real number is a number that can, that if you were trying to write it as a decimal, does not repeat or terminate, like square root of 3. But also in the subset of real numbers, you have your integers and your rational numbers. Real numbers are all numbers except for complex numbers. I told you in Section 10, 3.6, we have a couple of theorems. We started looking at the remainder theorem yesterday and factor theorem. Another good theorem that we're going to look at today is, well, how do we start to identify rational zeros when we have a polynomial that's higher than a quadratic? If we have a quadratic polynomial function, we know to use the quadratic formula. But how do you deal with it when it's a third and fourth degree or whatever? And another little helpful tool that we have for identifying our rational zeros or estimating where a zero is the intermediate value theorem. That's on page 377. Kind of at the same time that I do 3.6, I'm going to slide us into 3.7. We'll just go a step further with complex zeros of a polynomial function. All of our zeros of a polynomial function are not always real. You've already seen if you have like y equals x squared plus 4, y equals x squared plus 4, there are no zeros, right? Y equals x squared plus 4, parabola shifted up 4, doesn't cross the x-axis. So those would be called complex zeros. We'll look at the fundamental theorem of algebra. Another little theorem you can add to your vocabulary to entertain somebody Saturday night with your theorems, right? And then, hopefully today, and for sure by Lecture 10B, we will look at calculus-related factoring. And that is going to be a handout, and it will be posted on the website for those people who are taking it by video. And for you people in here, I'll pass it out to you. Okay, calculus-related factoring. Always a question on your test and always a question on your final exam. Calculus-related factoring. Okay, and the other thing I want you to be doing for tomorrow, it'd be lecture 11A. We're at the end of the chapter, and on page 394, we have another cumulative review, and it's so important that we keep going back, practicing, and also reviewing things that maybe we haven't even talked about before. Okay, the problems that you're leaving out in the cumulative review that are not objectives of this are problem number 10. That's just finding the center and radius of a circle, and it requires completing the square. We didn't make that an objective here. Number 11, we're leaving it out because we didn't test for symmetry. You could determine the intercepts. So let's determine the intercepts, but not do the test for symmetry. And then number 20, an objective of this course is not to determine algebraically if a function is even, odd, or neither. So we'll leave that out. Okay. So if you will have this worked out in great detail, and you guys in here, I'll take up your work like I did last time. We will go over these problems. Okay? So that will be in lecture 11. Got it? Questions? All right. Let's back up in section 3.6, kind of pick up where we were yesterday. We practiced synthetic division. And one of the nice advantages of synthetic division was we could hurry up and find out the remainder when we divided a polynomial function by x minus c. I'm looking at the remainder theorem on page 368. And we saw an illustration yesterday that when we divided by x minus c, we did synthetic division. the remainder that you got is actually equal to the value of the function at C. So I'm just going to send you back just real fast to yesterday. Yesterday we had a problem where we divided by x minus 3, x minus c. We did the long division, and we saw we had a remainder of 125. I then showed you how we used, this is the same problem, isn't it? Oh, I did a different problem. Okay, thinking I did the same problem, but I didn't. All right, we went to, say, problem number 16 in the book, and we said, okay, take this function, and we're going to divide it by -3. Or if you wanted to think about it, is this function divided by the factor x plus 3, because the factor, the remainder theorem said you're dividing by x minus c. So x minus a -3 is x plus 3. So we use synthetic division, and we remember we have to have a placeholder for every term of x, 6, 5, 4, 3, 2, 1, 0. Synthetic division, you brought down the 2, then you said 2 times -3, stuck it here, added. -6 times -3, put it here, added. But the interesting thing was, when you're right here, that is your remainder. And the remainder theorem says, okay, if you substitute in -3 into the original function, the value of the function comes out to be 0. And then the factor theorem says, hey, if that remainder is 0, then x minus the c is a factor. Everybody remember this from yesterday? Answer to that's yes. Okay.
I think you tried to show us something else.
I was going to try to show you something else, but I decided to pick a different problem because this was a 6-degree polynomial function. But I was going to tell you this little thing right here is called a depressed equation. I know that's somewhere in your book. Let me see if I can find the words. I remember seeing it the other day when I was looking at it. Okay, somewhere, I'm sure it's going to pop up somewhere. There, in here is the term depressed equation. And what happens is, if x plus 3 is a factor, then that means that the other factor is 2x to the 5th minus 6x to the 4th plus 3 plus x minus 3. And what we're going to do is look at some theorems. How do you continue to break this down to more linear factors and identifying zeros? Okay, was that something like what I was saying yesterday? Thank you. This thing is called a depressed equation, and you start working from there. All right? Okay, so we're in 3.6, and I also believe that there was still another warm-up problem I didn't do. Are you prepared? We looked at number 1, 2, and 3 yesterday. So let me do number 4. I believe I volunteered to do it. And then we'll look at all the theorems and we'll put it all together. Okay, so we're on Are You Prepared for 3.6. Okay, 3.6, page 378. Are you prepared? All right, number 4. All right, we're supposed to solve the equation x squared plus x minus 3 equals 0. All right, notice this is an equation. Would you call this a quadratic equation or a quadratic function? Equation. We don't see a y equals in there, so we have a quadratic equation. When we solve a quadratic equation, remember we have 0 on a side by itself, and then we try real hard to factor, except some of us prefer another way, right? Okay, and if you can't factor it, what are you going to do, everybody? Quadratic formula. Quadratic formula. And your quadratic formula solves for x. Remember, your a is 1, b is 1, c is 3. So we have x equals negative b, negative 3. Thank you very much. Negative b plus or minus square root b squared minus 4ac all over 2a. So we get negative 1 plus or minus the square root of 1 plus 12, 13 over 2. So to this quadratic equation, we have two real solutions. Negative 1 minus the square root of 13 over 2, and x is equal to negative 1 plus the square root of 13 over 2. Remember, these are called real solutions. Square root of 13 is a real number. It's a non-terminating, non-repeating decimal. Okay? But you can just plug and chug in your calculator and get a good approximation to what that number is. I didn't bring my calculator. And those would be the values of x that satisfy that equation. Now, I want to also point out to you that this is a second degree polynomial equation, which is a quadratic. And it was a second degree, and it has two distinct values for x. Two distinct values for x. They're both real values. All right. Are we good, everybody? All right, so we're going to turn through the pages of 3.6. Going to talk about all the theorems, and then we're going to have a problem that's going to illustrate everything, I hope. All right, so a lot of information in 3.6. Okay, 3.6. We've already talked about the remainder theorem on page 368. Let me just say it again, because your test question will say, use the remainder theorem to find whatever. And then your test question will say, use the factor theorem to do whatever. So you want to make sure you know what the names of these theorems are. All right, so the remainder theorem, you're going to have a polynomial function, and you're going to be dividing that polynomial function by x minus c. You can do long division or synthetic. I'm doing synthetic. That's quick. Whatever that remainder is when you divide, that is the same as the value of the function at c. So a test question would say, given this polynomial function, use the remainder theorem to find f at 4 or f at negative 7. Okay? Everybody got it? All right. Then the factor theorem says, okay, if f is a polynomial function, it's going to have a if and only if statement in the factor theorem. That means it doesn't matter whether you're at the first part of the sentence or the other part of the sentence. One way, it's going to work both ways. So if you happen to have x minus c as a factor, then you know immediately from this theorem that f of c is 0. If you have a polynomial function and you know f at c is 0, then you automatically know that x minus c is a factor. Okay, if and only if means if you know this part, then this part is true. Or if you know this part is true. Does everybody see how if and only if works? So if I tell you x minus 7 is a factor, what do you know about the value of the function at 7? If x minus 7 is a factor, what is the value of the function at 7? 0. Okay, if you know f at 10 is 0, what is a factor? F of 10 is 0, what is a factor?
X minus 10.
X minus 10. Okay? All right, got it? X minus the c. All right, and then they, at the top of page 369, they sort of break it down into two parts. The factor theorem really consists of these two separate statements. If you know f at c is 0, then x minus c is a factor. Or, if you know x minus c is a factor, then f of c is 0. Okay, so they sort of break it up and make it a little clearer at the top of page 369. Okay, we're on page 370 with another theorem. A polynomial function of degree n, where n is greater than or equal to 1. It has at most n real zeros. Did you catch the word has at most n real zeros? So if I have a fifth degree polynomial function, how many zeros, real zeros, x-intercepts, might I have? 5 or
0.
4 or 3 or 2 or 1. It's a fifth degree. Can I have 0 x-intercepts as a fifth degree? What's the end behavior of a fifth degree?
One goes up, one goes down.
One goes down, so it's got to go through the x-axis somewhere. Yes?
But how can it have 3 complex zeros?
We haven't done complex. We're still in
Well,
real. This is
saying.
just real zeros.
But if it's fifth degree, never mind. I'll just stay quiet until later.
Complex zeros, you could have either 2 or 4. Not an odd number complex zeros.
Yeah, that's what I thought.
Okay, that's the next section. All right, so we're in real zeros. All right, suppose it's a fourth degree polynomial function. Fourth degree polynomial function. How many real zeros might you have?
1. Could you have 1?
You could have 1.
Yeah,
What
more
else
than
could you
one.
have?
1, 2, 3, 4.
1, 2, 3, 4. Could you have 0 real zeros? Yeah, that's if you had like y equals x to the fourth plus 10. Y equals x to the fourth plus 10. Shifted up 4, 10. Shifted up 10, and it would have no zeros. If it's an odd power, you got to have 1 real zero, right? Because it's got to cross the x-axis somewhere. But if it's an even number, you have whatever that degree is all the way down to 0. Is that clear, everybody? All right, so that theorem is just saying, well, there's got to be some real zeros there if it's a polynomial. All right, at most. Of course, if it's even degree, you might not have any. All right, now we're looking at the rational zero theorem. How is it that when you have a polynomial of degree, well, if it's a quadratic, you know to jump right on the quadratic formula. So really, you're going to use this if you have a third degree or higher. But how is it that if you have a polynomial function, and if there are some rational zeros, how are you going to locate what they are? Rational zeros. Notice this word is rational. Remind me what a rational number is? Rational. It's a fraction, and what does the numerator and denominator have to be?
Anything with, denominator can't be 0.
Denominator can't be 0, and what else is it?
Integer.
Integers. Your numerator and denominator are integers. Denominator can't be 0. So this is not going to locate for you real zeros like square root of 3 or square root of 7, but the rational zero is going to give you potential zeros, and the ones that it will find are any rational zeros that you might have. All right, I'm just going to talk through this problem to give you the understanding of how this little theorem works, and again, the problem I'm going to do together with you in class will use that. Okay, I'm looking at example 3. This is a third degree polynomial function. Look at the instructions. List the potential rational zeros. Because if we have a function that has no rational zeros, you're not going to be able to find it using this theorem. So we're going to start out listing all the possible rational zeros. All right, your book uses little P's and Q's, and I'm going to explain how it is. Now notice P over Q is going to be in lowest terms. P and Q are over lowest terms. All right, here's the way it sets up. The P, you're going to look at all the integers that you can multiply together that gives you -6. And they listed them here. P is, you could multiply +1 times -6 or -1 times +6. You're looking at all the possible factors of 6. You can multiply 2 times -3 or -2 times +3. All the factors that you can multiply together to give you -6. Everybody good on P? Now the Q comes from the leading coefficient. P is always the constant term. Q is always the leading coefficient. So all the numbers you can multiply together, all the integers that you can multiply, these are integers that you can multiply together to give you 2, or plus and minus 1 and 2. Okay? Now, if your polynomial has any rational zeros, it's going to be the combination of the p's over the q's. So we're going to go to top of page 371. And basically all they did was look at all the p's and all the q's and come up with all the combinations. And what I normally do, and I will do it in the example we're going to do in just a second, is when I list the p's and the q's, I just put a little line underneath for division to get my p over my q. I just draw a little line like this. So you're going to have 1 over 1, 1 over 2, 2 over 1, 2 over 2, 3 over 1, 3 over 2, 6 over 1, 6 over 2. But then when you reduce all those, you're going to get that list on the next page. So P over Q, you'll just list your P and then your Q, and it's going to be plus minus 1 over 1, 1 over 2, 2 over 1, 2 over 2, 3 over 1, 3 over 2. Everybody see how that works? Now, what you then have the joy of doing is going through, and we will use synthetic division to look where the remainder is 0. Because when you have a remainder of equals 0, then you know x minus that divisor is a factor. Okay? So we will do that. Now, before we continue on, we're going to use the intermediate value theorem to make sure we don't get too far off in the wrong direction with our checking. All right, so hang in the book, keep going. Oh, by the way, at the bottom of page 371 is the word I was looking for and couldn't find. Depressed equation, depressed equation. I'll do that again when we're working through a problem. The depressed equation is what you're going to be left with after you have finally found a 0. Okay, the depressed equation. All right, so now we want to look at the intermediate value theorem. All right, when you look at the intermediate value theorem, we're going to use all this in the next problem that we're going to do together. On page 377, you're going to say this is a common sense problem, common sense theorem, once you see it. All right, let f denote a continuous function. Remember, if it's continuous, there's not going to be any breaks in the graph. No breaks in the graph. It's defined for all values of x. And if a is less than b, it just means that you're on your number line. A is smaller number than b. When you find the y value at a and you find the y value at b, remember f of a is a y value, f of b is a y value. If you find the y value at a and you find the y value at b, and if these y values are opposite sign, meaning one is negative, one is positive, one is negative, one is positive. If this curve is continuous and one y value is negative and one y value is positive, then your function is going to have to cross the x-axis to get from this y value to the other. So what it's going to say, well then f has at least 1, 0, one x-intercept between a and b. So what's going to happen here, if you can follow my logic, when we don't know what the real zeros, the rational zeros are, but we're doing synthetic division, and you remember your remainder gives you your value of your function. So if you're checking numbers and one remainder in synthetic division is negative, and you pick another number and the remainder is positive, then between those two values you divided by, which are your zeros, you know to go back in there that it's got to cross the x-axis somewhere in between. Okay, do you see how that's going to work? You're looking at those remainders, which are the values of the function. If one's negative, one's positive, then you know to go back in between those two numbers and you start narrowing in on your zeros. Okay, so intermediate value theorem, very important theorem that shows up again in calculus. Trying to remember if it's in 131. I know it's in the engineering calculus. Okay, a couple other little rules and regulations in this section. I told you there's a lot. We're on page 374. Page 374. If we have, this is theorem on page 374. Every polynomial function with real coefficients, no complex coefficients, but real coefficients, can be uniquely factored. What does it mean to factor? What does it mean to factor a polynomial? Factor.
Lowest terms.
Write it as a product, right? Remember when you have something like we did yesterday, 2x to the 6 minus 18x to the 4 plus x squared minus 9. That is not factored. We have terms separated by plus and minus. Factor means that we're going to take this and write it as a product. Write it as terms multiplied together. Okay? Factor, multiply. Okay, so the book says every polynomial function with real coefficients can be uniquely factored, written as a product, into a product of linear factors. In general, what does a linear factor look like? Linear factor. Linear.
X plus 2x,
Ax plus b. Okay, a linear factor, x to the first. And or irreducible quadratic factors. Okay, meaning that, okay, we know what a quadratic factor looks like. That would be something like ax squared plus bx plus c. But irreducible means that you cannot break it down to linear coefficients with real numbers, rational numbers in it. Okay, so you can't break it down any further with real numbers. All right, irreducible quadratic. All right. Here's another little statement right below that. A polynomial function with real coefficients of odd degree has at least one real zero. We've already said that. Why is that true? Odd degree polynomial function, why has it got to have one real zero? What's the graph of an odd degree polynomial going to look like? Yep, the end behaviors go in opposite directions, so it's got to go through the x-axis somewhere. So it has to have at least one real zero. Okay? All right, objective number 5 was not covered in this course, bounds of zeros. And I think we are ready to take a problem. I'm going to try to do everything to this problem, cover all these theorems we just talked about. If you think I'll leave something out, let me know. We're going to look on page 379 at problem number 40. And I'll probably make up a lot of other questions as we go along. F of x equals x cubed plus 8x squared plus 11x minus 20. Okay? All right, I can tell that you guys need to talk. So how about turning to your neighbor and tell your neighbor everything you already know about this graph just by looking at the function. Make a list of everything you know. Everybody's mouth moving.
The leading coefficient is
Yeah, to
1 degree of 3.
Yeah. Leading coefficients for different.
0.
Yeah.
Oh, Sam, I like what you just asked. That was a good word. You didn't know I was focused in on listening to you, did you? All right, so just start giving me a list. What did you say, Sam?
Degrees 3.
All right, degree
Okay.
is 3. This is a third degree polynomial function. How do I know that's a polynomial function?
Multiple.
It's y equals, that made it a function, but what else made it a polynomial as opposed to a rational function or some other kind of function?
It's
4x.
No, non-negative.
Your exponents are non-negative, 3, 2, 1, 0. Non-negative exponents. Okay, what else did you know about this?
The leading coefficient is 1.
Okay, leading coefficient equals 1. What else do you know?
In behavior.
The in behavior. And what is that?
Positive infinity, negative.
Okay, it's going to go like this somehow on the ends because that's a third degree, odd degree. The coefficient in front of the x cubed is 1. So somehow or another the ends are going to go like that, the in behavior.
Oh, how do you figure out the end behavior? I don't understand.
If it's an even degree, if the degree of the polynomial is even, the ends either always go up or they always go down. If it's odd, they got to go opposite directions. Okay? What else do you know? What else do you know?
You can find the possible rational zeros.
All right. Okay, hold on to that. What about, do you know a y-intercept?
Yeah.
Easily. What is it?
Negative 20.
-20. You know a y-intercept. What else do you know?
Domain.
The domain. Okay, what is the domain? Is there any values of x that would return an undefined y value?
Alright.
All real numbers. You can put in all real numbers. What is the most number of real zeros possible?
3.
3. Okay, so how many real zeros? Okay, I can have at most 3. What's the least number?
0.
Why?
Because it has to have 2 complex zeros.
No, we don't.
Well, I know.
Why do you say the least number you can have is 1?
Because they have to cross it somewhere.
It's got to cross the x-axis in a spot. Right. So it's an odd degree. So you could have 3 real zeros, 2 real zeros, or 1 real zero. You can't have none because it's got to cross through the x-axis here. What was your question? Yes.
I was gonna say it's gonna have 2 turning points.
2 turning points. It can have at most 2 turning points. Absolutely. Very good. Very good. Okay, anything else? X-intercepts. That's what we're going to look for. All right. We're going to jump on the rational root theorem, rational zero theorem, to help us find the rational zeros. Okay, let me make sure it's called. Okay, we're going to use rational zeros theorem to list potential rational zeros. All right, I guess I better write the problem down again. I've already lost it. F of x equals x cubed plus 8x squared plus 11x minus 20. All right, using the rational zeros theorem, and your test question will say, use the rational zeros theorem to list the potential rational zeros or find the potential, or find them. I'm not exactly sure what your test question is. All right, the p, we're going to list all the factors of p. Where did we find p?
Leading coefficient.
Nope,
Wait. Oh wait. That's the last one.
your constant term. This is where you're going to find the p. All right, what are all the numbers you can multiply together that's going to come out with a negative 20? Plus or minus 1 and plus or minus 20. What's the next one?
Plus or minus 2.
Plus or minus 2 with a plus or minus 10. What's the next one? Plus or minus 4 with a plus or minus 5. Okay? All right, let's find the Q. The Q is going to be all the factors of the leading coefficient. And you're really happy when you just see a leading coefficient of 1 there. All right, so that would only be plus or minus 1. Okay, so all of our potential rational zeros are of the form P over Q. So what I do is I just draw a little line right here, and I would do plus or minus 1 over plus or minus 1, 2 over 1, 4 over 1, 5 over 1, 10 over 1, 20 over 1, and I'm not going to rewrite that because that ends up being, as you can see, right here, because they're all over plus or minus 1. Okay? Now, what we want to know is 1 a 0, is negative 1 a 0, 2 or negative 2 or whatever. All right, I'm going to tell you something that I don't recall reading in your book, but it really helped me when I used to do this all the time. So, I'm going to do a little hint here. A quick check is to substitute 1 in F. All right? It's always easy to just put in the number 1 and very quickly see, that just means you're looking at F at 1. If that comes out to be equal to 0, then you've already narrowed your search in a hurry, right? All I'm doing is just substituting in. So if I put a 1 in, I'm going to get 1 plus 8 plus 11 minus 20.
Is that only if the Q is 1?
P over Q. This ends up being my entire P over Q.
You can substitute 1 anytime?
Oh, one's always going to be among your list,
Okay,
because
yeah.
you always have your factors of this, and one's
Yeah,
always
yeah.
got to be a factor.
Never mind.
Okay, so when you add 1 plus 8 is 9, 9 plus 11 is 20, 20 minus 20, that's equal to 0. Remember your factor theorem? It says if f of 1 is 0, we've already found one of the factors, correct? This is a really helpful little tool to always check out first before you start listing all these numbers. So, because we figured that out, let's start our synthetic division with 1, and we're going to look at our depressed equation to finish factoring this. All right, so we're going to do synthetic division. I've got 1x cubed, 8x squared, 11x minus 20. I already know that my remainder is going to come out to be 0 because I did my little quick check here. All right, so I'll bring down the 1. 1 times 1 is 1, add. 9 times 1 is 9, add. 20 times 1 is 20, add. And I got a remainder of 0, which is what I expected. Now, because I've got that remainder of 0, I'm going to be able to use my depressed equation to find my other factors, because I finally got it down to a quadratic. So therefore, f of x so far is factored to x minus 1 times, and what's this going to be? X squared plus 9x plus 20. All right, now once you get it down to a quadratic, I would not spend all my time checking all these numbers out looking for the 0. Once you get it down to a quadratic, you know how to solve for the rest of the values for x. And this factors to x minus 1, and I believe a x plus 5, and a x plus 4. So, this is all completely factored. I have it to its linear factors. And now you tell me all the zeros
1,
of
negative,
f. 1,
negative 5, and negative
5, and negative 4. I have 3 zeros. I have a third degree polynomial function, and I have 3 zeros. Okay? Could we easily sketch the graph now?
Yeah.
We could easily sketch the graph. Wouldn't we put along the x-axis 1, negative 5, and negative 4? Put in your y-intercept of negative 20. Do a little sign chart and just sketch your curve. Now looking at this and backing up, am I going to have a curve crossing through the x-axis, or am I going to have it touch the x-axis and turn around?
Crosses.
It's going to cross because
Negative. Positive.
Multiplicity.
Power.
okay, the multiplicity is 1. If I have even multiplicity on any of those, even multiplicity, it will touch the curve and go back, right? So this is just going to be a nice little curve that goes, whoops, it's going to go down, up, down. Is that right? Excuse me?
Can't the multiplicity be 3?
There's no multiplicity of 3. That would be if you had a 3 on the factor. Each of these zeros are of multiplicity 1. Each of these zeros are of multiplicity 1.
Because there's nothing on there.
Because there's no exponent other than 1 on each of those factors. Okay? Everybody good? All right. Now let's pretend that we didn't realize that we could just substitute the 1 in and immediately identify 0, the function. Okay? And what I'm going to do is pick 2 numbers and illustrate the intermediate value theorem. All right, so this is a pretend we were not smart. Okay, pretend we were not smart. We didn't substitute 1 in to see what it was going to work out to be. All right, so I'm going to pick some of these zeros that we see here. I'm going to pick 2 and negative 2. Okay, so I'm going to check x equal to 2 and x equal to negative 2 as potential zeros. All right? And I'm going to illustrate, this is to illustrate the intermediate value theorem. All right? So let's check out 2. All right, so it's 2. Our leading our coefficients are 1, 8, 11, negative 20. All right? So I'm just doing synthetic division. Bring the 1 down. 1 times 2 is 2. Add. 8 and 2 is 10. 10 times 2 is 20. Add. It's going to be 31. 2 times 31 is 62. And when I add, the remainder is 42. All right. So what that tells me, remember your remainder theorem, it says, had I plugged in 2 in the function, the value of the function is 42. The y value is 42. All right, so we would have known that wasn't a 0. Let's try negative 2. 1, 8, 11, negative 20. Bring down the 1. 1 times negative 2 is negative 2. Add. 6 times negative 2 is negative 12. Add. Negative 1 times negative 2 is positive 2. Add. By the remainder theorem, we know the y value at negative 2 is negative 18. Now, somebody tell me how the intermediate value theorem is going to tell you there must be a real 0 between 2 and negative 2.
There's a sign switch.
Because the y value at 2 is positive. The y value at negative 2 is negative.
So I have to pick between.
So it's got to cross the x-axis, right? Negative 2, negative 18 is down here. 242 is way up here. It's a curve that is continuous. Somewhere or another, it's got to cross the x-axis. So if you were not knowing what your rational zeros were and you came across this situation, then you go, okay, well, what numbers do I have between 2 and negative 2? Well, the only numbers you have would be a positive 1 and a negative 1. So you would check those out. So that way you narrow your search down. Is everybody good? Okay. Let's see if I've covered everything I need to. I believe that will take care of section 3.6. Oh, I wanted you to know that I did graph this function that we just worked with. on number 40 on page 379, and we found our zeros to be 1,
-5 and -4.
-5, here's -4, and -5 is somewhere in here. And the graph, although on Maple here, my units were a little bit too close, I hope you can see the red line went up above, so your graph really went something like this, up above and then down, and then like this. Okay, it's third degree, so your ends are opposite directions. I kind of exaggerated right there, but it's hard to see because of the way the units are, but it does go up above
What was
right
the
there.
negative y-intercept at the, on that?
This is set on, the y-axis here is really weird. That's at 50, 100, 150, 10, 20, 30, 40, 50. So there's your
your
negative 20.
Alright.
Yeah, your y-axis is by 50s, by 10s. And it looks like your x-axis is really spread out to thirds because there's 1, 2, 3, 4, 5. 0.2s. Okay?
Okay.
No, that's not true.
Pretty much impossible to draw on paper.
No, it's not impossible to draw on paper.
Yeah, but I'd already labeled my,
Yeah, yours is better than
Stuff.
this. I just ran it on Maple real fast. I didn't even notice Maple did the Y units by 10s and the X units so spread out. Okay, so you're good. All right, everybody good? Okay, let's go into 3.7. 3.7. Okay, and I'm on page 381. On page 381, and let's look at the objectives for this section. Now we want to get into complex zeros. Complex zeros. So we're still working with polynomials. We're looking at complex zeros, and then we have another little theorem called the fundamental theorem of algebra. And our objectives here is to use the conjugate pairs theorem. This has to do with when you have a complex zero, you're going to automatically know another zero. And then we want to be told some zeros of a polynomial function and ask you to find the polynomial function. And of course, we're going to then look for being able to find all the complex zeros of a polynomial. All right, so as always, let's jump on preparing for this section at the end of the book. And we are on page 385. 385. Are you prepared? And we have two questions, so we'll just divide right through the middle here. You guys get number 1, and you guys get number 2. Okay, and then we'll go over them. Are you prepared? Page 385. You get number 1. They get number 2.
I mean, difficult. did I outside?
What you guys
You got I.
Yeah, I got 1 plus or minus I.
That's what one plus or minus I.
1 plus or minus I.
Two equals I.
I mean, I did work.
Okay, so
How you doing?
got here and I equals outside, right? And then it's I.
No, see this would go I, and it'd still be the square root of 4. So 2 would come out, so it's 2I.
Yeah, that's what I did.
But I didn't get one.
Then you simplify it down to negative 2 plus or minus 2I.
So the answer is which
Repeat
is
what?
1 plus or minus.
So that's 4.
Alright, so the square root of 4 is 2. So that can come out, so it's 2I.
And the 1 after the end.
And both eyes. There are 2 answers. 2I.
Over 2. So then you just take 2 out on the top.
Okay. Then minus 1
Plus or minus
The square is 2.
over 2.
2. Gotta make sure I have the minus. Otherwise,
I see how, like, I just added them up, and like the negative 3 and the 3 cancel each other out.
then you're
Hello. That's down.
just making sure, because if you don't have
Okay,
there, it doesn't work.
because we only got about 5 minutes left on this tape, we're going to go over the Are You Prepared? Okay, we're on page 385, and the Are You Prepared?
Thanks.
All right, and number 1, it's talking to you about complex numbers. A complex number is of the form a plus bi, where a is the real part and b is called the imaginary part. Imaginary part. So a complex number, if b is equal to 0, then you really are just down to a real number. Okay? How do we define I? I is equal to
Square root of 1.
square root of
Negative 1.
negative 1. I is defined to be, this is a definition, I is equal to square root of negative 1. So what does that mean I square is equal to?
1.
Negative 1.
Negative 1. Because if you square both sides, that's just going to remove your radical, so I square is equal to negative 1.
Yeah.
Okay, so in the first problem, you first had to find the sum, which just meant that you were going to add 3 minus 2i to the complex number negative 3 plus 5i. So if you forgot, when you look back, you were told you always add the real parts and the imaginary parts. So 3 minus 3 is 0. Negative 2i plus 5i is 3i. So the sum is 3i. Okay, when you add complex numbers, you add real parts and then you add imaginary parts. Okay, then you had to multiply your complex numbers. 3 minus 2i times negative 3 plus 5i. And you're going to do just like you always did. You're going to FOIL them. Okay, when you multiply like 2 binomials together. So 3 times negative 3 is negative 9. 3 times 5i is positive 15i. Negative 2i times negative 3 is positive 6i. And negative 2i times 5i is minus 10i squared. Is that what you guys got in this group?
On the last one.
Okay. Yeah, when you multiply I times I, you get I squared. Okay? Now, what did you tell me I squared is equal to? Negative 1. So this is negative 9 plus 15i plus 6i minus 10 times negative 1, which makes that a positive 10. Everybody good? Okay, now we're ready to finish. We're going to add the real parts together. Negative 9 plus 10 is 1. And then we're going to add the imaginary parts together. 15 plus 6 is 21i. How's that, everybody? Good? Remember that? All right. Let's go to problem number 2 real fast before we run out of time. X squared plus 2x plus 2 equals 0. You've got a quadratic equation. Couldn't factor it. What did you do?
Quadratic formula.
Jump right on the quadratic formula. X is equal to negative b plus minus square root b squared minus 4 times the a times the c all over 2a. Oops, 2a is 1. All right, so we get negative 2 plus or minus the square root of 4 minus 8 over 2. Is that what you got? Guess I better rewrite this. X equals negative 2 plus or minus the square root. 4 minus 8 is negative 4 over 2. And we're supposed to solve it under the set of complex numbers, so how did you deal with that negative 4?
Took out an I.
Okay, you brought an I out, and the square root of 4 is
2.
2, so we get negative 2 plus or minus 2i over 2. Square root of negative 4 is I times the square root of 4, which is 2i. Okay, now how do you simplify that quickly?
Take out a 2.
Factor out a 2 out of the numerator, you get negative 1 plus or minus I over 2. I'm doing the factoring, and now the 2's divide out. And we have x equals negative 1 plus I, and x is negative 1 minus I. Those are not real numbers, so if I were looking for zeros of a function, we wouldn't have any real zeros, okay? All right, we got to stop there, and we'll pick up later. Good. Then maybe we'll have hundreds on the next test. All right, welcome back, everybody. We're at Lecture 10B, and we had just started Section 3.7. We're still working on polynomials, but now we want to look at polynomials when some of our zeros are going to be complex numbers. And so we have a little theorem called the conjugate pairs theorem. And we want to be able to write polynomials when we're given zeros and know their multiplicity. And then we want to be able to find all these complex zeros. Okay, and I do hope you realize that we have a very selected set of exercises. There are plenty of polynomial functions that have real zeros, and it would be hard for us to really find those real zeros. Wake Sam up. You there? All righty. Okay, so at the end of the last lecture, we had just finished Are You Prepared? And I want to point back to the last problem we did when you had a quadratic equation to solve for x, and you had to use the quadratic formula. And we had 2 values for x. And both of these values for x are complex numbers. And the interesting thing about these complex numbers is one is negative 1 plus I, and the other one is negative 1 minus the I. So one's a plus I and one's a minus I. These two numbers are called, who wants to tell me? Complex conjugates. Complex conjugates. conjugates. Look at the E. Complex conjugates. A plus BI and A minus BI are called complex conjugates. And what's going to happen is when we have a polynomial function, if it has one complex zero, well then the conjugate is also going to have to be a complex zero because it would have been found by the quadratic formula. Okay? So the deal is when we have a polynomial function, if we find one complex zero, then automatically its conjugate is going to be a zero. Okay, and that is probably called the conjugate pairs theorem in your book, which is on page 382. Page 382. The conjugate pairs theorem. If f of x, let f of x be a polynomial. This is a polynomial function whose coefficients are real numbers. Okay, so we have a polynomial function, real number coefficients. If the complex number a plus bi is a zero of the function, then the complex conjugate a minus bi is also a zero of the function. And all that does is that comes right out of the quadratic formula. That's where you're getting them from, the quadratic formula. Okay? All right. Let's look at the other theorems here, and then we're going to work a book. I'll work a couple problems. The fundamental theorem of calculus. Excuse me. I did that in my calculus class. Fundamental theorem of algebra. Sorry, we're on page 381. There is a fundamental theorem of calculus, by the way. But this one's of algebra. All right. We're talking about a complex polynomial function. Well, a complex polynomial function, if you look a little higher up, is going to be a polynomial function, but the coefficients are complex numbers. Complex numbers. Now remember, a complex number is of the form a plus bi. And if it so happens that the b is 0, then the a is a real number. So if you say complex coefficients, you mean you're open to real numbers, complex numbers, integers, whatever. Everything is fair game. All right? So to come up with a complex polynomial, this is all kinds of polynomials, and the coefficients could be complex numbers. Of course, they could be real numbers. They could be integers or whatever. So this is taken in everything. Okay, so the fundamental theorem of calculus says if you have a complex polynomial of degree n greater than or equal to 1, it's going to have at least one complex zero. All right, at least one. So whatever the degree is, if you've got, and remember, a complex number, a complex zero takes into account real numbers because the bi part could be 0. Okay, so if you have a degree greater than 1, you got at least a 0. It may not be real, it may be complex. Okay? All right, and of course then you found out if you have a complex 0 with the imaginary part, then it's going to have to occur in pairs. Okay, because you have conjugates with that. All right, so those are the two biggie theorems from this section. So this is actually going to go pretty fast here. We're going to go to page 385, and we're going to work some problems right out of the book. Page 385, and the first problem we're going to look at is number 10. Page 385, number 10. I'll show you what it looks like. This problem number 10 says, I'm going to tell you that we have a polynomial function of 4th degree. The coefficients are real numbers. And we are supposed to find the remaining zeros of the function when they give us 3 zeros. And we're going to take that a step further. We're going to actually form a polynomial function, having that. That will take care of problems. Which number am I doing? 10? That will take care of the next group of problems at the same time. All right? So, number 10, we have a polynomial function, degree 4. We're told that zeros are 1, 2, and 2 plus I. So we have a 4th degree polynomial function. We just learned that if we have a complex zero of the form a plus bi, we're immediately going to know another zero. What would that be?
2 minus.
Its conjugate. Also, 2 minus I is a 0. Because if one complex number, a plus bi, is a 0, then its conjugate is also a 0. Everybody good? Okay, now let's write a polynomial function with these given zeros. All right, so we'll start out with f of x equals. All right, if 1 is a 0, what is a factor? If 1 is a 0, what is a factor?
X minus 1.
X minus 1. If 2 is a 0, everybody, so you verbalize it. What is a factor?
X minus 2.
Yes. If 2 plus I is a 0, what is a factor? X minus, we'll do a little parentheses here, 2 plus I. Okay? And if 2 minus I is a factor, then X minus 2 minus I is a factor. Okay, this represents one polynomial function with those zeros. If I wanted to represent every polynomial function, we put a little a right here, where a is not equal to 0. Remember, that's just going to do a vertical stretch for you by having an a there. All right, but here's all your zeros. All right, let's go a little bit further on this. So x minus 1 is a linear factor. X minus 2 is a linear factor. I'm going to take a second to multiply out x minus 2 plus I times x minus 2 minus I. And let's see what that looks like. Okay, we want to take a second and multiply that out. All right, there's a little trick of the trade here that makes life a little easier. So I'm going to show you what that is. If you were going to multiply this out, the easiest thing to do is first distribute your negatives. So we'll have x minus 2 minus I. And you have x minus 2 plus I. All right, I'm going to call this trick of the trade. All right, now you could multiply x times each of those, negative 2 times each of those, negative I times each of those, and combine your similar terms. But the little trick of the trade that makes this easier is to regroup. This is the trick of the trade. So now we're going to regroup and write this as parentheses x minus 2 minus I. Now nobody's telling you have to do this. I'm just going to tell you this makes life easy. And x minus 2 plus I. Does anybody see why this is going to make the multiplication really easy now?
Minus 2 squared.
It's the factored form of the difference of two squares. This is like a minus b times a plus b. A minus the b, a plus the b, which when you multiply it out is just a squared minus b squared, correct? So it's just going to make life a little easier and less mistakes. Nobody says you have to go with my little trick of the trade, but it will be easier if you do. All right, so if I multiply this out, it will be equal to x minus 2 squared minus I squared. All right, well, we know how to square x minus 2. That's x squared minus 4x plus 4 minus, and what does I squared equal to? I squared, negative 1. So this is x squared minus 4x plus 5. Okay, this is called a irreducible quadratic. This is called an irreducible quadratic, meaning that you cannot factor it to linear factors with real numbers. You cannot factor it to linear factors with real numbers. X squared minus 4x plus 5 is called a irreducible quadratic. All right, everybody with me on this? Okay. So now what I want to tell you is that this polynomial function can be written as a times x minus 1 x minus 2 times x squared minus 4x plus 5. All right, so the words I want to use is, this is written as linear and irreducible quadratic factors. All right, I want to show you where this is in your book. All right, then I'll come back and answer your questions about this. All right, I'm on page 384 in your book, page 384. There's a theorem there. There's so many theorems in these last sections. Every polynomial function with real coefficients can be uniquely factored, means written as a product, over the real numbers into a product, multiplying, of linear factors and or irreducible quadratic factors. Irreducible quadratic just means that you've got complex roots to your quadratic. Okay, no real solutions there. Okay? All right, so let's back up and make sure everybody's good with the example we just did, number 10. The question only asks you to find the remaining zeros. So if you have a fourth degree, you're going to have 4 zeros. They may not all be unique. And if you have one complex zero, you immediately know its conjugate is a 0. I ask us to go a step further and come up with a polynomial function, which I really wanted to get to factored as linear and irreducible quadratics. I put the A here because you can have a zillion polynomial functions with these zeros. They just might go up higher and down lower, but they have the same zeros. The first two factors are linear. When I put in the complex numbers, we multiply those out to come out with the irreducible quadratic. It only has complex zeros. So I have written this function as the product of linear and irreducible quadratics. How's it, everybody? Good? Questions? Anybody? Okay, the next example we want to look at is number 22. Number 22. This is on page 385. We're going to form a polynomial function with real coefficients, having the given degree and 0. Okay, we have degree 5. We have zeros 1, and that 1 is of multiplicity 3. And we have 1 plus I as a 0. All right. I wanted to get back into that word multiplicity. All right, so we want to form a polynomial function. All right, if it's 5th degree, I'm looking for 5 zeros. They may not all be unique, and clearly it's not if 1 is a 0 of multiplicity 3. One of the zeros is 1 plus I, so that accounts for 4 of the zeros. I need a 5th zero. You quickly tell me what it is. 1 minus I. Because complex conjugates. They always occur in pairs per zeros. Everybody got it? All right, so you work ahead of me. I want you to write the polynomial function with degree 5 and those zeros. Check and see how your neighbor's doing. All right, get me going. What is it? X minus 1
To the third.
to the third power. 1 is a 0 multiplicity 1. What else?
X is minus parentheses 1 plus I,
Good.
and X minus X plus X minus 1 minus I.
Okay. All right, that is one polynomial function with those zeros. We put a little a right here. We'll have all polynomial functions. Okay, x minus 1 is called what kind of factor? X minus 1 is called what kind of factor? Starts with a L. Linear. A linear factor, x minus 1. Even though it's raised to the third power, the x minus 1 is linear. All right, let's work down and get the irreducible quadratic. Okay, and we'll go with my little tricks of the trade here. Let's distribute the 1. Okay, I just distributed the 1. All right, since I'm forcing you to do my trick of the trade, what's your next step?
Regroup.
Regroup. Regroup, because now it fits the form a minus b, a plus b. Factor form a difference of two squares, so you have x minus 1 squared minus I squared. Okay, x minus 1 squared is x squared minus 2x plus 1 minus, and remember I squared is, say it so you don't ever forget, negative 1. So we have x squared minus 2x, and 1 plus 1 is 2. Why is this called an irreducible quadratic?
Can't go no.
You can't factor it with real numbers. Okay, so you can't factor it any further. Okay, so f of x equals a times x minus 1 cubed times x squared minus 2x plus 2. So we have it written as a product of linear factors and irreducible quadratics. Okay, now I want to take this question a step further. Everybody all right? So this is extra, not in the book. This means you're getting more than your money's worth. Okay? Suppose that you were told to find a fifth degree polynomial function with these zeros, and this is no longer number 22, passes through the point, let's just do 2, 8. I hope I didn't make up something that didn't work.
You fill it in.
Okay, what is that going to allow me to do if I say it has these zeros, it's a fifth degree, and it passes through this point?
Find an
it's going to allow me to find A, the one unique polynomial function that passes through this point. All right, now because I just made this up on the spot, I hope it works. We'll see. All right, the y value is 8. We're solving for A. X is 2. So we got 2 minus 1 cubed times 2 squared minus 2 times 2 plus 2. So 8 is equal to A times. Did I do that right?
Yeah.
2 minus 1 is 1. 1 cubed is 1. 2 squared is 4. Oh, I picked good numbers. 4, take away 4 is 0, plus 2. So A then is going to be equal to 4. So the unique polynomial with those zeros and passing through those points is, we'd put that 4 right back in there. 4 times x minus 1 cubed times x squared minus 2x plus 2. Everybody good? Questions? All right, we're going to look at our grand finale for today, which is problem number 24. 24. And you have lots of homework problems. Number 24. The grand finale for today. We still have calculus-related factoring to do. Don't pack up yet. You were ready to leave. What? Okay. Number 24. Use the given zero to find the remaining zeros of this third-degree polynomial function. Okay? We're given a third-degree polynomial function. We're told 1 0. Let's find the remaining zeros. All right, number 24. G of x equals x cubed plus 3x squared plus 25x plus 75. And we're told a 0 is minus 5i. All right, this is a third-degree polynomial function. Are you expecting at least one real 0? Third degree. Yeah, because the ends of the graph go opposite directions. It's got to pass through the x-axis. So we got to find the other 2 zeros. All right, do you already immediately know one of the other zeros? 5i. This is like 0 minus 5i, so its conjugate would be 0 plus 5i. All right? Now, how do you propose? There's 2 or 3 or 4 different ways maybe to go about doing this, and one way is easier than all the others. How would you go about trying to find the other 0? Suggestions? Tell your neighbor. You won't tell me. Tell your neighbor. How would you go about finding the other 0? I'm not listening. Go ahead and tell your neighbor. What do you think? Well, it's okay if you're wrong. At least you're thinking. What did you think?
When you set it up like synthetic division and try to like factor it out or whatever.
Okay, that's one way. Use synthetic division. And so you would be dividing by minus 5i into 1, 3, 25, 75. That's a perfectly fine way to do it, but that's the hardest way. What would you do?
All rational zeros.
Oh, okay. I hadn't thought about that way. He wanted to use the rational zero theorem. All right. That would work perfectly fine, assuming that you have a rational 0. So you'd look at all the factors of 75, which are 1 and 5 and lots of other things, and 75. Okay, that's a good way. That's equally hard. Give me another way. We're looking for the easy way. We want to be lazy.
Factor.
Factor? All right, so let's see what you're going to factor. Tell me.
I don't know. Just putting it out there.
Hey, I like what you're saying. Keep going.
That y equals 0. Can you do it? Y
Didn't you
equals
just-
0? G of x equals 0. And then, no, you can't. Never mind.
Well, if you're doing g of x equals 0, it's not a quadratic, so you can't
Yeah.
use a quadratic formula. But I think you're hot on to something, so keep going. If I told you these are zeros and you wanted to start factoring, what would it look like? If this is a 0, what is a factor?
Positive 5i. Or x plus 5i.
Okay, x minus negative 5i is plus 5i, and x minus 5i, and then there has to be another factor there, right? Okay, we're hot. We're doing good. Okay, let's write that function g of x. X cubed. Y'all are doing good, even though I know you're tired. This is equal to, I'm just rewriting it, x plus 5i times x minus 5i times something else here. All right, let's play with this part. This is going to be the easiest way, although your other ways were okay. I'm just looking for an easy way. Now what are you going to do?
Multiply it.
Want to multiply this out? All right, let's do that. So this is equal to, so if you multiply x plus 5i times x minus 5i, you're going to get x squared minus what? 25i squared, and we got that times that little question mark there. And I squared is negative 1, so negative 1 times negative 25, so we got x squared plus 25 times the question mark is equal to x cubed plus 3x squared plus 25x plus 75. All right, pretend this is a little algebra equation. How would you solve for this question mark?
Couldn't you, like, do synthetic division?
Well, synthetic division is the divisor x minus r, but maybe long division
Yeah, long
would be good. All right, so you're just going to divide both sides by x squared plus 25. Right? And let's go with long division. X squared plus 25 into x cubed plus 3x squared plus 25x plus 75. All right, x squared goes into x cubed how many times?
Once.
Good old x times. So x times x squared is x cubed, and x times 25 is 25x. Okay, remember you subtract. Don't forget to distribute your negative. All right, so the x cubed subtract out. I'm going to bring down the 3x squared. The 25x's subtract out, and I'm bring down the 75. Okay, x squared goes into 3x squared how many times?
3 times.
3. So 3 times x squared is 3x squared plus 75. When you subtract, what's my remainder?
None.
0, which is what you're expecting it to be, because we were looking for a 0 of the function. Remember, your remainder theorem now says f of minus 3 equals 0, or x plus 3 is a factor. Hold that thought 1 second. So, our question was to find all the remaining zeros. And I'm just writing our function in factored form. Okay, so our zeros, according to the question, our zeros are 5i, negative 5i, and negative 3. Okay? But if we wanted to write our polynomial in factored form, linear and irreducible quadratics, x squared plus 25 times x plus 3, a linear and an irreducible quadratic, would be how we would write it in factored form.
I thought synthetic division was what's a substitute for long division?
Synthetic division is a substitute for long division as long as your divisor is x minus r. Synthetic. That's a x squared plus 25. You can't use synthetic division unless your divisor is x minus r. So I had to go with long division here. That's a x squared plus 25. It would have to be like x minus 25 to go with long division. I saw you had a
I
question?
was going to ask, could you have used synthetic division
Right.
also? That's all.
Right. The only time you can use synthetic division is x minus the r, not a x squared. All right. Everybody good? Feel good about this? Answer to that's yes. All right. Let's have some fun with calculus-related factoring. I forgot to pass these out to you guys. Here they are. To take that and pass them back. All right, this is a supplement to your textbook, calculus-related factoring. All right, and this is going to be fun and games. You're going to enjoy doing it. Fun and games. You don't believe me, do you? All righty. It's a very calculus-related topic because what is going to happen is in calculus, you're going to be taking derivatives of functions using what is called a product rule and a quotient rule. And once you do that in calculus, you're going to have to completely factor some of the things like you see here at the bottom. You're going to have to do that because that's going to be the next step to identifying local maximum and minimum points in your curve. So in pre-calculus, we're going to get you right to the step that if you've taken the derivative, we're going to show you how to do the rest of the algebra to completely factor. And then you'll be really good in your calculus class. All right, so the illustration that I have on the top of this page is to just recall the good old distributive property of multiplication over addition when you were told to factor. Remember, factor means write as a product, but because I have AB plus AC separated by a plus, I have just two terms. So I need to write as a product. So using that distributive property in reverse, everybody says, oh, you just factor out an A and you have B plus C, right? And now it's a product, A times B plus C, so it's factored. All right, if you know that, you can do every problem on this page. Here's my example. Suppose that we're told to factor x plus 1 times b plus x plus 1 times c. Now notice that I have two terms because terms are separated by the plus. In the first term, I have two factors. One factor is x plus 1 and the other factor is b. Just like up here at a times b, I have two things multiplied. In the second term, I have two factors, x plus 1 and a c. Just like up here, I had two factors, a and c. And when you factored it, you brought the common factor outside the parentheses. So I have two terms, and I want to write it as a product. So when you look at both of these terms, what factors are common to both? Everybody says
X plus 1.
x plus 1. So we're going to bring the factor x plus 1 outside the parentheses, and inside my big set here, I will have two terms. So x plus 1 times what gives me x plus 1 times b? And everybody says b. And x plus 1 times what gives me x plus 1 times c? And everybody says
C.
c. So this is now completely factored x plus 1 times b plus c. Everybody good? All right, I'm going to keep building on this before we jump on the sheet. Questions yet? All right, the next example. I told you this was fun. Factor. And my example this time is x plus 1 squared times b plus x plus 1 times c. Oops. Yeah, that's what I wanted. Okay. Again, I have two terms because these are separated by that plus. Terms are separated by pluses or minuses. In the first term, I have the factor x plus 1 of multiplicity 2. I have the factor x plus 1, and I have the factor b. And in the second term, I have the factors x plus 1 and c. I notice that x plus 1 is in both terms. What is the greatest power on that factor? Actually, it's the lowest, but I'm going to say the greatest factor common to both terms. So that really is the lowest exponent. What factor is common to both here? X plus 1 to the first. That's the greatest factor common to both, which ends up being your lowest exponent. Alrighty. Just bring my little plus right here. Okay, tell me right away what goes here.
Plus 1 times B.
X plus 1 times b. And what goes here?
C.
C. So if you multiplied all this out, you would have xb plus b plus c, and that would not factor any further. I have now written this completely factored. Everybody good? All right, we're just going to carry over to the sheet, and I want you to just look at this sheet and decide if you're going to be brave and go hard or you want to start out easy. I want you to pick a problem 1 through 8 and tell me which one you want to do.
Let's do an easy one and do a hard one.
Do an easy one and then do a hard one. Okay, let's do number 4 and then we'll do, say, number 8. How's that? Let's go with number 4 off the sheet. Number 4 we'll call easy, just in case you're not realizing it is. 5 times x squared plus 4 raised to the 4th times 2x times x minus 2 raised to the 4th plus x squared plus 4 to the 5th times 4 times x minus 2 cubed. Now, I just want to tell you that these problems were made up by taking some functions using the product rule to find the derivative. So in calculus, you're going to work a problem and you're going to have this huge mess, and you're going to have to factor it. So my little hint, the instructions are to factor completely. My hint is clean it up. Clean up. Because it looks like a huge mess with a 5, and then you got a 2x over here, and then you got the x squared plus 4 to the 4th. So I would say clean up by saying 5 times 2x to get 10x, and then we have x squared plus 4 raised to the 4th, and x minus 2 raised to the 4th. And then over here we're going to have plus a 4 times x squared plus 4 raised to the 5th, and an x minus 2 raised to the 3rd. Okay, cleaning up just meant that I multiplied those monomials, 5 and the 2x together. All right, does everybody see what I did? All right. Now, how many terms do I have here? Terms. 2. I only have 2 terms. Terms are separated by this big old plus right here. Did you say 2?
I said
Plenty.
plenty.
You only have 2. I guess 2 could be plenty, yeah. All right. So what we're going to do is set up a big set of parentheses, and I'm going to just put this little plus right there in the middle. All right, so let's start with constants. We have a 10 and we have a 4. What is the greatest common factor to both 10 and 4? And everybody says 2, right? 2 divides 10 and 2 divides 4. So we're going to factor out a 2. All right, so I like to do it a little step by step. So 2 times what's going to give me the 10? And everybody says 5. And 2 times what gives me the 4? And I have a little 4 right here.
2.
How about a 2? A little 2 right here. Okay, so I've taken care of the 10 and the 4. Everybody good? All right, now I see a factor of x in the first term, but I don't see a factor of x by itself in the second term. So there's not a common factor there, so I'm just going to go put the x with the 5. Okay? Now, in the first term, I have 4 factors of x squared plus 4. In the second factor, I have 5 factors of x squared plus 4. So, how many can I pull out of both terms? 4 of them. So I'm going to come outside parentheses and put an x squared plus 4 to the 4th. All right, so now, if I'm thinking about multiplying back, I've already pulled out all 4 of those in the first term. When I go to the second term, how many are left? 1 factor. Okay? Alrighty. Now when I go back in, I see 4 factors of x minus 2, and I see 1 factor of x, 4 factors of x minus 2 in the first term, and 3 factors of x minus 2 in the second term. How many can I pull out? 3. So we'll do x minus 2 cubed, and that leaves me with 1 factor of x minus 2 for the first term, and I pulled them all out in the second term. Is there a question this far?
That's not too bad.
Not too bad, thank you, that makes me feel good. Alright, so factor means we're writing everything as a product, so all we have to do now is clean up in the big set of parentheses. Okay, so I'm going to multiply in here so I can see what else is going on. 5x times x is 5x squared minus 10x. And now I have a plus 2x squared and a plus 8. All right, let's see what that looks like. So we have 2 times x squared plus 4 to the 4th, x minus 2 cubed. 5x squared and 2x squared is 7x squared. And I have minus 10x, and I have a plus 8. Now I get the privilege of deciding, is this an irreducible quadratic, or will it factor further? Did somebody have some insight here? Let's see, we'd have to have a 7x and an x, and I need to come out with a negative 10, 2 and 4, 14 and 4, yep.
Oh, yeah.
Nope, that's not going to work. All right, let's check the discriminant. B squared is,
Would you switch the 2 and the 4?
switch the 2 and the 4.
No, couldn't do it.
Couldn't do that.
14.
All right, let's check the discriminant. B squared is 100 minus 4 times 8 times 7. That's negative, right? The b squared minus 4ac, the part that goes under the square root symbol, 10 plus minus square root. That's going to be less than, that's going to be a negative number. 4 times 8 is 32, 32 times 7, so it can't be factored any further. So that's an irreducible quadratic. Always check out your discriminant real fast and
If you
you
were
have
to
it.
use the quadratic, you'd end up with something I, wouldn't you?
Complex numbers, right, and we're just
You know,
factoring,
Just leave it the same?
we're factoring over the set of real numbers here. Okay? All right, everybody good? That wasn't too bad, was it? Just takes a little practice. Let's look at, because of time,
Wait, so that could be, you could solve it to I?
if you used a quadratic formula, you could come up and factor it with complex zeros in there. You could, but you don't want to. All right, I'm going to look at problems 9 through 14 real fast just for the interest of time here. You get to do all these others and have fun. All right, notice in 9 through 14 we have rational functions, and we're going to use, it's just a double dose of what we just did, but we're going to go back and remember that when you have a times b over a times c, and of course a not equal to 0, what does that simplify to? B over c. So we're going to have to completely factor the numerator, completely factor the denominator, and hope things divide out. Okay? You want to do 13? We will do number 13 for you. Do what?
I don't know.
We're going to look
Whatever's
at
harder.
No, okay, we'll do number 13 off the sheet. We have 3 times x plus 2 squared, x minus 3 squared, minus x plus 2 cubed times 2 times x minus 3 all over x minus 3 raised to the 4th. Okay? All right, and our instructions are to factor completely and simplify. Simplify just means we want it reduced to lowest terms. Okay? All right. So we want to completely factor the numerator, and the denominator is already in one factor there. X minus 3 just happens to be a multiplicity 4, so we're already finished with it. I'm glad you picked that one. You made it easy. Oh, they all just have one factor. All right. In our numerator, we have the number 3 and we have the number 2, and there is no common factor there, correct? So here's my big set of parentheses, and I'm going to bring down the minus right here. And so we have a 3 in the first term and a 2 in the second term. All right, I have 2 factors of x plus 2 in the first term and 3 in the second term. How many are you going to pull out?
2.
2 of those. X plus 2 squared. Okay, so I've pulled all of them out of the first term, and I'm left with 1 factor in the second term. Does that make sense, everybody? If you multiply back, you're going to be right back here.
Ran off the page.
I ran off the page. There you go. Thank you very much. All right. In the numerator, I have 2 factors of x minus 3, and I only have 1 in this term. So how many am I going to pull out?
X minus 3.
1 of them. So that leaves me with 1 more factor in the first term, and I've already taken care of that. All right. Are we good so far? Everyone? All right, do you already see a place that something's going to simplify? This is all multiplied. How about that x minus 3 over x minus 3 to the 4th? One of those is going to divide out with one of those, right? When you have a over a to the 4th, that ends up with 1 over a cubed, right?
And then take out the 1.
Yeah, I'll take that one off. All right, so let's see what happened on the inside. So we got x minus 2 squared, and let's distribute the 3. We have 3x minus 9 minus 2x minus 4. Be careful distributing your negatives. Over x minus 3 cubed.
It's x plus 2 on the numerator.
How did it go from
Oh, thank you, x plus 2. I was so worried I was going to miss a negative in that second factor there. My brain was working on that. Thank you for keeping me straight. All right, let's see what we got here. X plus 2 quantity square times 3x minus 2x is 1x, and negative 9 minus 4 is negative 13, and all of this is over x minus 3 cubed. And we are so happy because we have completely factored and simplified. Okay, I've got it written, everything as a product. 3x minus 2x is 1x, negative 9 minus 4 is negative 13. That's not too bad. It looks worse than what it is, wouldn't you agree? So the deal is, when you look at one of the problems, be sure you recognize your terms. They're separated by pluses or minuses. And you're just using the distributive property in reverse to pull out the common factors to both. And when you have rational expressions, you completely factor numerator, completely factor denominator, and work down. Can you do it? Say you can, and we're done for today.
We can do it.
You can do it? All right, we'll stop right there. Make it a great day, everybody. Oh, don't forget your cumulative review for tomorrow.
Is it worth 10 points?